So welcome everybody to the session, invited session number 5, called The Best of Both Worlds, Combining Deep Learning and Modeling. And the idea of this session is basically to bring together deep learners and modelers. And I think our presenters actually are both. And so I'm really looking forward to the talks where we can say, okay, what can we really gain by bringing in different kinds of modeling data analysis strategies. And for not wasting any time, so we go to our first speaker. I'm happy that we have Chris Rackauckas here from MIT, Pumas-AI, and Julia Computing at the same time. So Chris, the Zoom room is yours.
Yeah, thank you very much. So yeah, what I'm going to be talking about today is Pharmacometrics-Informed Deep Learning with DeepNLME. As mentioned, I'm part of MIT, also Pumas-AI, which is a pharmacometrics firm, and also Julia Computing, which is a modeling and simulation based firm. And these actually all three come together for making DeepNLME possible. So let me start by just kind of giving a quick outline, right? Essentially, the idea is that mixing equation discovery with modeling it essentially gives a workflow that will revolutionize the field. So what I'm going to start with is just an overview of scientific machine learning, about how mixing domain knowledge with machine learning can give you better predictions. And then I'm going to move over to DeepNLME, which is the specific to pharmacometrics form of scientific machine learning. So scientific machine learning is model-based, data-efficient machine learning. The idea here is that you need to have a certain amount of knowledge in order to actually get accurate predictions. But that knowledge doesn't necessarily need to come from data, right? When you do machine learning, you're essentially trying to learn everything from the data. With scientific machine learning, you're mixing in these scientific models as some kind of prior information, so that way, you can reach that requisite knowledge with having less data. And so what all of these techniques try to do is they try to bring in these mechanistic models to try to build a hybrid that then gives you a more efficient way of doing this learning process. The basis of the approach is what we call the universal differential equation. So the idea here is that a neural network, what the core of a neural network actually is it's a universal function approximator. So for example, it could approximate any possible function, Rn to Rm, epsilon close if you have enough weights inside of there. Right. And you can formalize that and you actually prove that. Right. So as an object that can stand in for missing functions and give them a discrete parameterization, what you can do is you can say, well, if I know part of my mechanistic model, I can mix part of the mechanistic model that I know with differential, those are going to be differential equations. I can mix those with parts of the model that I don't know, represented by a neural network that is capturing an unknown function. And you can train this unknown function against data. So here what we show is that, in a lockable terror model, we assume, hey, we know some of these linear interactions. Bunnies tend to grow, wolves tend to die, and something happens between bunnies and wolves, right? And this neural network represents something seems to happen, right? And what you can do then is you can train this neural network to capture, from the data, what this missing interaction should be, and then perform a symbolic regression to actually discover, well, given all of the knowledge that we had prior about what we knew about the model, what symbolically should have been there, right? And you can do that just by saying, let's regress this neural network back down to a mechanistic form. And what you find is that this ends up being a very data efficient way of discovering models while incorporating all the prior knowledge you had. And so let's actually dive into it a little bit so that way you can see it in action. This example I'm going to go into first here is just using an epidemic model, because epidemics are kind of in vogue right now. And so here we're saying, oh, here's data from a epidemic model, so we know the actual underlying model. We take we can run it for a bit, and we say, if we just train a neural network inside of a differential equation for 21 days, how does it extrapolate? Right. And so here's a neural ODE. And as you can expect, basic machine learning methods like neural ODEs and such, they fail to extrapolate beyond the data set. Right. That's machine learning just cannot have that property of going behind the data that it actually tried to learn off of. Now, what if you do this hybrid approach? Right. What you can do is you can say, well, I can have an SEIR model, right? So I can have an SEIR model with hospitalization. I can know a lot of these parameters inside of there. What is the rate of recovery from COVID-19? Well, we know it takes about a week, right? And what is the percentage of people that are hospitalized, right? There are a lot of these parameters that you can kind of guess and get ballpark in the right ballpark. And the part that you cannot get in the right ballpark is, how does exposure work, right? Because exposure is dependent on which state you are in. If you're in the US, it's dependent on which country you're in. If you're not in the US, it depends on whether people are wearing masks, whether people are protesting. There's so many different things that affect exposure, and that it's really hard to come up with a model beforehand, right? And so what you can say is that I know there's something epidemic-like going on here, right? I have a model of an epidemic, but there's something that within this model that I don't know. Replace this unknown part of the epidemic model with the neural network, and let's see then how well we're able to learn from data and be able to guess what should be going on in the near future. And so here we train once again only on 21 days worth of data, but we're able to extrapolate about an extra 20 days, whereas the pure neural ODE or physics-informed neural networks have no extrapolation capabilities. Right. So this is this idea of imposing this prior structural knowledge. Well, let's go one step further, right? So the neural network is a very highly parameterized structure, right? And so it's good to go to a very highly parameterized space, kind of let your optimization find what your solution is, and then collapse it back down to a mechanistic form. It's essentially symbolic annealing in function discovery space. So here we're letting the energy go up. We're finding what are the missing functions in our model, and now let's anneal it back down and say, well, let's perform a symbolic regression, right? So we have these tools that automatically take a neural network and transform it into a symbolic form that is very similar to what the neural network inputs and outputs would be over a given space. And if you do this, what you find is that it extrapolates much better, right? It's not perfect. You can definitely see it's diverging, but it is something that has more of the properties of a mechanistic model, because you've actually used this to find a mechanistic model off of just 21 days worth of data. And the reason why it's been able to work so data efficiently is because you've pre-assumed a lot of things about epidemic models in the form, right? And so this is the general idea here, right? You use as much mechanistic modeling that you have. You then use neural networks as a way to be able to discover missing terms, and then you do a symbolic regression after doing this discovery to be able to bring it back to mechanistic terms, right? Either just because less parameters ends up having better properties like extrapolating better, but also because this gives you actual mechanistic predictions, right? This is predicting that the exposure term is not dependent on U3, where U3 is hospitalization, which is basically saying that the model is taking into account that people who are hospitalized are not those who are exposing people to COVID-19. It tends to be the people who are not hospitalized and who have this disease, right? And so you can, from this kind of symbolic regression, then you get actual mechanistic hypotheses out of this form of extrapolatable low data machine learning. So this is a lot of really nice properties that standard machine learning doesn't have, and this is what we then try to employ in practice. And so does this actually work in real models? Well, when we went to a real epidemic data, what we're able to find is that we can do such a thing with something we call the QSIR model, where the QSIR is a SIR model with a learned quarantine term to try to figure out, how should we be taking, something that is possibly a very complex model, but describing it as essentially a SIR with added nonlinearities inside of there, where we learn the nonlinear correction terms. And when we do this, we're able to get really good forecasting, where we do this against real data, or if we do this, say, if I have a 9-compartment SIR model and I want to collapse it down to a 3-compartment model with the nonlinearity, this is you're able to basically train on small amounts of data or just small parts of the time series and extrapolate forward quite well in a way where these pure neural network techniques like neural ODEs are not able to, because they do not have that kind of prior knowledge of epidemic structures, right? And you can then do this to the next level. So here's a Bayesian universal differential equations, where you can start to say, well, I'm going to do a Bayesian optimization of the weights of the neural network within the differential equation. And what this then gives you is it gives you a probability distribution over the possible neural networks defining your missing functions. And then you can symbolically regress those and say, well, what is the probability that I'm missing a quadratic term in here? What is the probability that I'm missing a interaction term inside of here? And then you get these probabilities of what's the percentage of the time that the symbolic regression is giving you different types of terms as the output. And then you can use this term lambda, the sparsification, to kind of find, what is the right level of sparsification that is then giving you, something that is some realistic predictions, and go back to the lab and try to verify, do I have an upregulation term here, or do I have this interaction term that this neural network is telling me I have, right? So this brings it then to the probabilistic space. Instead of trying to say, well, you're missing this term, right? Now it's trying to say there is a 95% chance you're missing a quadratic term, a 5% chance that you're missing a cubic term, and most likely there's something quadratic, so some interaction in the model going on. So all of this is built on top of the scientific machine learning open source software organization. There's a whole set of tools where if you go to sciml.ai, you'll find that all of these tools are automated and pretty efficient now, right? So it's built on these fast differential equation solvers, which are, this is something that we're since 2017. You can find all these talks showing that it's, 50 times faster than SciPy, 50 times faster than MATLAB, 100 times faster than RSD solve, with the real claim to fame that it also outperforms a lot of the C and Fortran codes. But go see one of the other talks on that. Now, the entire model fitting process is fully automated. So if you just say, this is the model that I have, you stick neural networks in for the missing portions, and you ask it to find the model, it'll run this training process, and it'll iteratively be finding the weights of this unknown portion of the model. And then if you run the symbolic simplification, it'll actually spit out as LaTeX what the missing parts of your model are. And if you do this with a Bayesian form, it'll give you the probability of having different forms of the missing model. And the speed really takes into account a lot of different factors, right? So if you try to use something like sundials from C++, right, what you'll find is that, this ends up doing model fitting about 3 orders of magnitude faster. You can see our recent update to a paper on sensitivity analysis about why we're able to do this. Essentially, it comes down to a difference in the adjoint calculation plus a implementation which uses reverse mode automatic differentiation as part of the way the adjoints and the gradients are defined. So there's kind of a technical detail in there that I'll skip. But this ends up, it ends up being something that's around 10 times to 100 times faster than competing things like something like torch stiff EQ for neural ODEs in PyTorch, right? So I'm rushing through the computational details because you can find a lot of other talks on that topic. I want to get directly to the part on DeepNLME though. So where we've been going with this is we've been using this throughout industry, right? So this is where, kind of switch hats from academia to the industry hats that I have on. So for example, we've been working with NASA Launch Services who changed their Simulink models over from Simulink to Modeling Toolkit and saw 15,000 times acceleration using these tools, the faster differential equation solvers, the symbolic numerics mixed with the equation discovery. Also, Pfizer has been one major user over the last year with the 175x acceleration in the preclinical aspects using the GPU accelerated differential equation solving. One major application has been Pumas, which is this pharmaceutical modeling and simulation in the clinical pharmacology regime, where this is all built on the same tool set using the same tools for model inference. And this, of course, had the very, at this point, it's, say kind of famous use inside of Moderna at becoming the go-to tool in 2020 for doing a lot of the clinical trial acceleration to be able to get that, down in less than a year. So with this background, then we're this connection of we have all these ways to do automated model discovery, but we also have the tools that are actually being used for inference within models that are happening in the true clinical pharmacology space. Is there a way to combine these two worlds, right? And so this is where we get to DeepNLME. Right, and the core of the idea is, so a nonlinear mixed effects model is a model where you say, I know some covariates about the individual, right? So I know some things about I know a few things about, like, say, the weight or the sex. The core thing about covariates is that they're information about the patient that you know beforehand. So the moment they walk in the clinic, you know this part, right? And from your covariates in a nonlinear mixed effects model, you derive, you have a structural model, which I also call pre, which gives you these dynamical coefficients, right? So these are things like the rates of your dynamic model are given as a function of your covariates. And then from your structural model, you then have the rates of your dynamical model, right? So in the end, what this means is that if you know all of the parameters inside of this whole model, then directly from someone walking into the clinic, you can know, well, if they are a male instead of a female, then the rate at which they will metabolize the drug will be this much faster instead of this much. And so therefore we should change the way that they're dosing by X or Y, right? Now the real core issue here, though, is that there's two core issues. One is that how do you actually fit and find what the parameters of this model are, right? So this is the nonlinear mixed effects model training regime, which by building with the software Pumas, where we solved well. The core idea is that you want to find these fixed effects theta and the random effects eta such that the expected value of eta is equal to 0. The intuition there is that the eta are subject-specific fudge factors, and thetas are in some sense an average effect. And so if you can find if you can try to make most of the predictive power be in your fixed effects, then you get the best prediction with only knowing the covariates, right? Because the random effects, the etas, are different per subject, and so they're not very informative for something like patient predictive dosing, because it requires a little bit about the etas require a little bit about the specific patient, whereas the thetas are true for anyone who has these properties like this weight or this sex, right? And now so the core issue here of how NLME is done, which I'm skipping over the math of this, is you want to find how to make it so that way as much predictive power is in the thetas and as least as possible is in the etas, because you could just say every single patient is different, but you'd get fitting parameters, but you'd have no predictive power from that, right? Now, one of the core issues in nonlinear mixed effects modeling, though, is where the heck does this structural model come from, right? And where the heck does this dynamical model come from, right? So it turns out that one of the main things that makes pharmacometrics kind of constrained right now is that you have to come up with a reasonable structural model, and people have only really tested a few things. So like, how does your drug metabolism change for different weights? How do male and females differ? There's been enough clinical trials on that aspect. There's some things around ethnicity, some things around what fast metabolites dependent on one specific gene, right? But there's really only 5 covariates that people use in practice, and because people don't really know how to put together the structural model. So is it possible to automatically discover what these models are, what this dynamic model is inside of a nonlinear mixed effects? And so the idea here is that if we want to make it so that way we can actually discover what these models are, you can use the same idea as before. So the same ideas of the universal differential equation by covering pieces of the model that you don't know and making them into neural networks, basically having them be parameterized functions as a neural network, and then doing the symbolic discovery from the learned neural network. And the key here is that the weights of your neural network should be treated as a fixed effect. So that way they are not patient specific, and instead something that is directly learned from the covariates. So that way, just from knowing the covariates, you can predict through the neural network and know how a given patient will act the moment that they walk to the clinic. This means that you have to integrate your neural network training process with the full NLME fixing, full NLME fitting software, which is a deal in itself, right? Because the other, the competitors in this NLME fitting space are software from the 1970s and written in Fortran. And so really having this brand new, tool for nonlinear mixed effects modeling is giving us a unique opportunity to do a neural network infused version of it kind of for the first time. And so what this really looks like then is you can develop these models where you say, I have some parameters that are fixed effects that live in the neural domain, and I'm going to, just to automatically learn from from the data, what some of these pieces in the structural model are. So what your clearance and what some of the dynamical weights should be, given different individuals with different covariates and different data series from the clinic. And then once you and here this is assuming a dynamic model, but you can also learn that as well. And what this will then do is automatically learn and train these neural networks. You can sparsify them down, and they'll give you some, similarly give you these symbolic descriptions of what should have been going into the model and what you should have been writing here in the first place. Now, the real interesting part about this is that this lets you use a really large set of covariates. So, for example, an idea for a covariate can be, let me use an image, right? An image is a full, thousands, every single pixel is in some sense a separate covariate, or you can use genomic data, right? You no longer have to know how to go from the genomic data to a prediction of what the drug clearance is. You can automatically learn, well, from this series of hundreds of thousands of values, what should that connection be? And the symbolic regression will then tell you, well, these are the 5 pieces of the genome that actually are affecting this drug metabolism, right? Because remember, once you symbolically identify it, it gives you a prediction of what the mechanistic model is. And so this technique is now being currently tested on clinical trial data, right? In some sense, it's just an extension of the universal differential equation, right? It's using the universal differential equation idea inside of a nonlinear mixed effects platform, using the nonlinear mixed effects likelihood for training the neural network weights. But now this gives you essentially a whole way to be able to perform automated discovery covariate models, find out which covariates of an individual are predictive for drug metabolism. And this is now being starting to be put into production. So thank you very much. This is hopefully a pretty good overview of where DeepNLME is at in practice. I wanted to make sure that we mix some of what the core technical details and going on behind clinical trials is. I can't mention all those, so I mixed a bit of the high level that's being done in the open academic world, right, to be able to kind of give a flavor of why mixing prior information with neural networks is giving you better predictions, and how mixing neural networks into nonlinear mixed effects modeling is then allowing people to do this universal differential equation idea within clinical trial analysis. So yeah, thank you very much. And I think that is about time to take the questions.
Thank you for this very exciting presentation. Yes, we have several questions. I'm going to read them from the chat. So the first one is by François Messier. It is, thanks a lot for the nice presentation. One of the reasons for fitting mechanistic or semi-mechanistic models is to make use of the model parameters because we think they have some biological meaning, e.g. growth rate. How to interpret the parameters from a deep NLME approach so that they are actually actionable? Thanks for your thoughts on this point.
Yeah, so that's why the symbolic regression as a step in this process is quite nice, right? So the symbolic regression, transforms, you basically, it's a form of simulated annealing, right? You go out to a very, a neural network can learn every function. After you've learned a function, then you try to find out what is the best fitting function that can do. There's a few reasons for doing it as a 2-step process. One reason is because if you just try to say, oh, let me just add every possible linear and quadratic term and do a local optimization, you'll find that you easily get to local minima that don't make sense. Also, that's very hard to sparsify, right? So if you try that, you'll see. And so what we really do is we use this neural network as an intermediate to be able to hold on to a computational form of a function that we didn't otherwise know, right? And so you grab this intermediate, and then you do this in sparse regression to then be able to say, oh, this is a possible mechanistic model, right? And when you're back to this form, it's basically giving you a guess of what are possible mechanisms that you could have been missing, and what are the coefficients related to that, right? So it can then get you back to that mechanistic understanding. So the two pieces that tie back together into this, right? You probably don't want that to be purely deterministic. You probably want it to be probabilistic, right? And so the Bayesian UDE extension gives you a idea of, oh, there's an 80% chance of having this term, 20% chance of having this term, to be able to give you more uncertainty quantification in the model discovery process. And then when you finally get to the nonlinear mixed effects portion, right? The real key here is that if you try to do, if you try to come up with a pure symbolic discovery of the structural model, it's really difficult because this loss function is a very specific object, right? You want to do a maximum likelihood such that the expected value of the random effects is equal to 0. And so there's a very specific computational way that you have to do the optimization of the parameters in here. And so, but once again, right, if you treat your neural network, weights as fixed effects, you can do the same loss function to be able to then hold on to this missing function as a neural network. And then separately, after you've gotten a computational form of this missing function inside of this whole prediction process, then you can do a symbolic regression and go back to predicting, well, the mechanism, it should be like this, and here are the rates of it. And that's actually a really key point too, right? Because when we're doing the automated discovery covariate models, right, you might, one of the main aspects of how we're using this is, you can take a whole genomic data, right? And you can say, I have 100,000, different possible genes that might be predictive of how the person's how their metabolism is changing to this drug. But when you do the symbolic or regression and symbolic discovery, it'll basically say, these are the 5 predicting factors, right? It'll say that these are the 5 SNPs that tell you whether someone is going to be reacting to the drug differently, which, that then brings you back to mechanistic predictions, right? That says, go look at those SNPs, go separate those people in clinical trials, get that information, and really see whether there is this true effect between them. And that might actually affect how we should be doing personalized patient healthcare, right? So yeah, the neural networks on their own do not have this possibility, but that's why we mix this neural network approach with the symbolic regression. Really bringing the two together really improves both of the approaches together. Yeah, great question.
Thank you. The second question is by Solish Chakravarti. Is nice work. 2 questions. One, high-dimensional nonlinear coupled ODEs as applied in PB, PK, PD, QSP has identifiability issues. Mm-hmm. Would DeepNLME with more parameters due to the neural network have similar issues? So this was the first one. And the second one is, in NLME, there are principled approaches to propagate the uncertainty in data to uncertainty in model parameter estimates. Can similar approaches exist for DeepNLME to quantify model parameter uncertainty?
Yeah. So the first quick question is a great question, right? So so Pumas is one of the softwares that has automated some structural identifiability analysis to tell you whether your parameters are identifiable, right? And I can tell you in advance that the neural network version will never have identifiable parameters, right? It's because what the neural network is actually giving you is it's not giving you reasonable parameters, right? The neural network, remember, is trying to be a stand-in for a missing function. Right. And so there's actually a very interesting mathematical question here, right? Of what does functional identifiability mean, right? Because a neural network with many different weights might still represent the same function. In fact, if you do this training process on this lockable Terra, you'll find that with different random initializations, it will always give you different neural network weights, but all of those neural network weights represent the same quadratic function, right? And so, in some sense, this is identifiable as a neural network as a function, even though the parameters of this model, which are the weights of the neural network, are not identifiable. Now, how can you actually formalize that and mathematically prove what does functional identifiability mean and when should you expect it? That is not something that we've fully solved right now. I can show you a bunch of numerical examples where a lot of DeepNLME examples are functionally identifiable, but it is a very interesting mathematical question to figure out how to really formalize that question mathematically, right? So I think that will be one of the keys to the extensions of this approach in the very near future, and we are working on this aspect. So that was the first question, right? Then parameter identifiability is not really the issue. It's function identifiability that's the issue when you start using this approach. But the second question was, what was the second question again?
About propagating uncertainty.
Oh yeah, so propagating of uncertainty. I mean, like the methods for propagating uncertainties and calculating the confidence intervals I mean, we include them in Pumas because they're kind of standard, right? Using things like Fisher information matrices, though they really are making a assumptions that do not apply even to nonlinear mixed effects models, right? They really only work when you have some kind of almost linear type of differential equation. So I'll say that that a lot of these metrics that people use are already a little bit suspect just to start. Though one way that people have been kind of working around this, right, is by using Bayesian techniques for doing the learning. And it turns out if you use the Bayesian fitting processes of Pumas with the neural networks embedded within them, it essentially will do the Bayesian DeepNLME or the Bayesian UDE process. So Bayesian DeepNLME by default, where what it'll do then is it'll give you probability distributions over missing mechanistic terms and predictions of confidence intervals by using the as the Bayesian posteriors, right? Now, exactly how do you do this, right? What were your prior distributions? Well, here the prior distributions are the standard GLOW-ROT distributions that people generally take initial conditions of neural networks from, and then you can kind of specialize your prior distributions a little bit more if you have different prior information about where the prediction should be. But yeah, so we're going through a full Bayesian, Hamiltonian Monte Carlo and variational inference approach for doing uncertainty quantification of Bayesian DeepNLME. Yeah, because I mean the standard techniques based off of Fisher information matrices and stuff, they're barely it's really skeptical to use them on nonlinear mixed effects in the first place, and so using it when you have a neural network involved is basically not a good idea. Yeah, great question.
Okay, thank you. Unfortunately, we can take the 2 remaining questions, but maybe Chris, if you see them online, maybe we can find some time for this later. So thank you once again for the great presentation. And
thank you.